let's start. So last time we developed all the building blocks of the second quantization formalism, and I first want to remind you, and then what we do today is to see how we can express physical operators using this language, and later we'll also see how we actually do calculations of concrete problems. So, this description using the second quantization involves defining a vacuum state we denote it as 0, and with respect to this vacuum state, we define a set of annihilation and creation operators, where lambda are some set of single particle quantum numbers, like momentum, spin, lattice state, harmonic oscillator, index doesn't matter, some quantum numbers. And the annihilation operator is such that acting on the vacuum gives 0. It annihilates the vacuum, and therefore any many-body state for arbitrary particle numbers can be expressed in terms of states that are created by applying the creation operators on the vacuum. So the Fock space, which is the Hilbert space we are going to work with, is spanned by the basis states of the form N1, N2, etc., where the Ni's or N lambdas are some of the relations, and so the state N1 and 2 can be generally expressed as a product of quantum numbers, normalization factor, A lambda dagger applied N lambda times on the vacuum, and the lambdas in this product are represented here. So each state lambda is occupied by occupation L lambda, and this is an explicit way of how to write it by using the operators A lambda and A lambda dagger. And now what we know about these operators is that their algebra, they obey some algebra rules, and that depends on the statistics. So for fermions or bosons, we define the parameter zeta, that is -1 and +1 for fermions and bosons respectively, and the annihilation and creation obey the following rule. This is for fermions. For fermions, they are anti-commutators. These are lambda delta lambda lambda prime, and A dagger is 0. For bosons, we have instead commutation relations. And that's all. Now, using these commutator relations, we can manipulate any application of a product of A's and A daggers on some state can be manipulated by shifting operators around and using these commutation rules. And that allows you to see what a specific operator does when it applies on a specific state. Now, so we know how to write any arbitrary wave functions in this Fock space. It is simply going to be a superposition of many such basis states. And if we also know how to write operators, any operator acting on the many-body system in terms of A's and A dagger, then we have everything we need. Okay? So we are still missing this last part, which is how to write a general operator. And because we want to describe many-body systems, we want to allow for physical operators that describe processes or physical quantities that involve more than one particle. Okay? Okay. So, and we'll see how to do it today. Now, one thing that we did last week at the end, I want to just remind it because today we're going to use it. Is a change of basis. So when I'm writing my creation and annihilation operators, I use some quantum numbers, and in principle the formalism doesn't care what is lambda as long as it's some quantum number that describes a complete set of states in the single particle system. But it may not be a very, I mean, you have some freedom to choose it depending on your problem. For example, when you have a system where everything is translational invariant, then momentum is a good quantum number, so you want to use K vectors. For other problems, you may want to use local operators that act on a point, and etc., depending on the problem. So you want a way to go from one basis to another for choosing, having the freedom to go from one representation to another. So so this is the rule we got last week, change of basis. Let's say that I had some basis of lambdas, and I want to switch to a new basis that I will call lambda twiddle. Then a lambda twiddle dagger can be expressed as sum over lambda of lambda twiddle a lambda dagger, and of course it's very easy to see that the annihilation operator will be, let me write it explicitly, just putting a dagger on everything, I get that the annihilation operator is given by the Hermitian conjugate of the matrix element, going from lambda to lambda prime, A lambda. Okay? So, and this overlap between, or inner product between lambda and lambda twiddle is nothing but a unitary transformation from one basis to another, element of a unitary transformation. And a particular example for such change of basis is if we had our lambda and we want to switch to what I called here generally lambda twiddle, is going to be the real space coordinate R. Okay, so we want to go to a basis of local coordinates, or vice versa. Okay, any transformation has of course the inverse transformation. It's a unitary transformation. So the application of this general formula to real space is that the creation operator for a particle at position R, which I'm denoting by psi just for bookkeeping of the fact that it's an operator that has units of 1 over square root of the volume, because we want psi dagger psi is going to be a density operator, so it has to have units of 1 over the volume. Okay, so it has, unlike the A's which are dimensionless, this has dimensions. That's why the convention is to express it differently, and I'm just applying this formula. So it can be expressed as a sum over lambdas of lambda R. Okay, I'm just copying this formula. But what is this? The inner product of state lambda with R, or the complex conjugate of A. It's the wave function. It's actually the spatial description or the spatial representation of a wave function of a particle at state lambda. Okay, and it's actually phi star, because phi is a bracket with the conjugate. Okay, and of course similarly psi R, which is the annihilation, is going to be just phi times A. Okay, so therefore, if we, for some reason, we start from a problem that is expressed in real space in terms of local operators, we know how to convert it to any basis. Okay, that's the prescription. Okay, great. So, having all that in mind, let me now go to the main business of defining operators. How to express various kinds of operators that we are going to be interested and will appear in any Hamiltonian. Eventually, the most important operator for us is going to be the Hamiltonian. Okay? But the Hamiltonian may have different terms contributing to it, describing potentials, kinetic energy, and interactions between particles, which is the most complicated object. So we're going to classify operators according to how many particles they act on at a time. And the first type is going to be called one body operators. Okay? what is a one-body operator? It's a set of operators that, of course, it can act on a system of many particles, but it acts on each particle separately. Okay, so this is the simplest thing. In fact, you already used it when you did, for example, statistical physics of quantum particles, of quantum many-particles, but when you thought about something like an ideal gas, then you wrote an expression for the energy of the Hamiltonian that is just a sum over particles of objects that act each on one particle only. Okay? So in most general way, we can, if we're using the language of first quantization, one-body operators are objects that can be expressed as something like that. Okay, O1. Okay, O(n). Okay, well, this little O(n) is an operator that acts on particle n. So in this writing, I'm keeping track of the particles. Okay, I have capital N particles, and n is an index that counts them, and the capital N that we are going to be interested in is typically macroscopic, or it can be macroscopic. It doesn't have to be, but it can be a macroscopic number. But the fact that you can write it in this way makes it very simple, especially in systems of identical particles. So when we have identical particles, okay, let me give you an example for such a one-body operator. This is the kinetic energy. In fact, this is something we already used in the first lecture in this course, right? Kinetic energy, for example, of atoms in the linear chain is nothing but a sum over n of the kinetic energy of the individual particles, which are this, right? Or actually, let me just write it as okay, so it's Pn, where for each particle, Pn is the momentum operator, which in real space is minus I h bar d dx, etc. Okay? So now suppose that we have capital N identical particles, and all of them have the same kinetic energy. Suppose this is the situation. Then what will be the total, what will be the kinetic energy? If we apply it on such a state, what will we get? We're going to get just the sum over kinetic energies of each. But if they are identical particles and all of them have the same kinetic energy, we'll just get the kinetic energy of a single particle multiplied by the number of particles with this thing. That's all, right? And remember, you used it all over the place when you did statistical physics for ideal gases, right? Okay, so and another example for one-body operator is total potential energy, which we can write as a sum over n of V of xn. Okay, so V is some potential, and let's assume that it's you have a set of particles in some external potential, and all of them see the same potential. However, the values of a V depend on the coordinate, right? So So each particle experiences a potential that depends on its own coordinate, and the total potential energy is just the same. Okay? So this you already seen. Another example is the spin. If you have particles with a spin, we can think of the total spin as a sum of n of little Sn. Okay? Yeah. Okay, so we can think of a total coordinate. We can think of many examples, but basically that's it. These are the examples. But notice that now, depending on the problem that you have in mind, you can, if you want to work with these operators and apply them on some many-body states of identical particles, you better choose a basis that is the most convenient. What will be this basis? Now it depends on the problem you want to study. For example, if you have a free gas and the energy, the Hamiltonian contains only kinetic energy, what is the quantum number you want to use to describe the single particle states?
K.
It will be K, the momentum, right? So, so then you're going to express, it's better to choose, when I switch to second quantization, which is what I want to do now, I better choose the creation and annihilation operators in the K basis, okay? And similarly, if you want the spin, it's useful to choose, let's say, a basis of sigma z is diagonal for each particle, and then, yeah. Okay, so, so most generally, we want to choose a basis where what I call the little o, if I look at its matrix element between two single particle states, here the lambdas are single particle states. So in the second quantization language, they can be created by applying just one creation operator on the vacuum. The matrix element of this little o, which acts on only one particle, between lambda and lambda prime. It can be generally anything, but if we choose the basis lambda to be such that O is diagonal, then it's going to be given by, there's a delta, lambda prime, and the diagonal elements of little o, I'm going to denote them as O of lambda. Okay?
What is lambda prime?
Lambda prime is just the difference. So if lambda is a set of quantum numbers, okay, it's like k and k prime. If k is a good quantum
And
number.
on the right side, you have the prime only in the delta?
No, I'm saying that I'm choosing. I mean, generally, this can any operator can be is some matrix in any operator that acts on a single particle is a matrix in this basis.
Yeah, sure.
Right?
I mean, on the right side of
Yes.
the question, the prime is
These
only on
times. What's the question?
the prime is only on the delta?
It doesn't matter. You can switch it. You can leave it as it is. But you tell me. That
Yeah, right. So yeah.
You can leave the. You can leave it. It doesn't matter.
Once you enforce the delta, when you enforce the delta, lambda has to be equal to lambda, right? Okay, that's why it's actually I want to define it with only one index. That's the whole point. Okay, so these are just the diagonal elements and the others are 0, okay? Okay, so now, however, what I have a many-body system. I have a many-body system, and when I apply the one-body operator, is just a sum of such things, and when I apply it on a state where I have not one but n lambda particles in state lambda, what will I get? So let me write it down. I take this operator as defined, and I apply it on an arbitrary, not arbitrary, sorry, on a state that, let's start from the simplest case, that I apply it on a state that has a finite occupation only of state lambda, but it's occupied by not one, but n lambda particles. Okay? So there are n lambda particles, all of them are in one state. Okay? What will I get when I apply O1 on this? Let me first, before that, let me ask you a simpler question. What happens if I apply this, what I call the On, on a state lambda? Okay, and the index n is an index of a particle, but the particles are identical, so I don't care which one it is, okay? But what will I get?
So lambda.
Because it's diagonal, exactly, I will just get O lambda times lambda, right?
Mm-hmm.
Therefore, if I apply O1, which is a sum of many such contributions, acting on each particle one by one, and I apply it on a state with n lambda particles in the state lambda, what will I get?
O lambda to the power.
I will get, so each particle will give me O lambda. But I have n lambda such particles, all of them have O lambda. So what's the total?
N O lambda.
Exactly, it's just n lambda, or let me write it opposite ways. It's O lambda, n lambda times n lambda, right? The eigenvalue, it's again, once again, n lambda is also an eigenstate of O1 with eigenvalue given by O lambda times the number of particles occupied in this state. Okay? Great, so now we can go to the next stage. The next stage is to apply it on the most general state in the basis of Fock states, which is a state where I have a set of occupations of different lambdas. Okay, so O1. Now I apply it on a state that has n, let me write it lambda 1 and lambda 2. And here I have many lambdas, but they are independent. Each of them is occupied by its own occupation. What will I get here? Exactly. So actually, whenever I apply this operator on a part, all the particles in lambda 1 will give me O lambda 1 times n lambda 1. All the particles in n2, etc., etc., and they are independent. It's an independent sum. So what I'll get is just a sum over I, where I is the index of all the states that are included here, O lambda I times n lambda I times exactly the same sorry, okay. All right, so this equation tells me that all the states that span the Fock states, the Fock space, are eigenstates of a single body operator with eigenvalues given by this. Okay?
That's only for the basis.
This is for the base. This is all for the basis of Fock states. That's right. But now you know what you get if you have now a state that is not a Fock state, but it's a superposition of Fock states. But it's a superposition. This is, since it's a linear operator, it will give you for each component. You know exactly what it will give, and therefore you can see what it will. Of course, it will no longer be necessarily an eigenstate, right? But I mean, generally it will not be. But you know what will happen if you apply on it, and you can then calculate its matrix element with some other state, and you can calculate expectation value, right? Okay, so if you like, in a sense, by writing this identity, you already know how to write any matrix element of O1 in Fock space, right? Because what will be any matrix element? A matrix element in Fock space is a sandwich between some n prime, n prime lambda 2, and O1 with this one. Okay, this is the most general matrix element. But since the right-hand side, it's an eigenstate, it gives you the eigenvalue times the state. And the eigenvalue is a number that you can take out of the sandwich. You just get the sum of an I, O, lambda I, and I, times the sandwich of n lambda 1 prime, and lambda 2 prime, and n lambda 1, n lambda 2, okay, etc., etc. And actually, you know what is this? It's a product of deltas, right? Okay, excellent. So in fact, we have a way of characterizing all the matrix elements, and therefore fully characterizing the operator O1 using this identity. Okay? But now I want to rewrite it in terms of a second quantization notation. What does it mean? It means that it's some combination of A's and A'. Okay? These are the only operators I'm allowed to use. These are my Lego blocks, if you like. Okay? So I want to write it in second quantization, but this identity has to be obeyed. So I need an operator, I need a representation that will give you the same eigenvalues, okay? And I actually know how to to do it because I can now erase all this. Okay, so you already know from the problem of harmonic oscillator and from the phonons, phonon problems that we mentioned in the beginning of the course as an example, that there is an operator, let me denote it by n lambda hat, okay, the hat is to denote an operator, which is a lambda dagger a lambda. And I'm claiming that this operator deserves the name number operator. Okay? Why? Because what this operator does is counting the number of particles at state lambda. Okay? So it's the number operator for state lambda. Why? Because if I apply it on, let me again apply it first on a state which is really exactly like in the harmonic oscillator problem, except that it's true also for fermions, of course. I can take a state that that is occupied by n lambda particles, identical particles, all of them at state lambda. Let me write it actually explicitly. It's a lambda dagger a lambda acting on the state n. What is the state n? We saw already that up to a normalization factor, we can write it as a lambda dagger to the power n lambda acting on the vacuum. Okay? Now, and this is something that I think you're going to show in your next homework, but I think you have already seen it. I think you already saw it for the harmonic oscillator, even in your undergraduate. What do I get when I apply it? First of all, how do I deal with it? Okay, let's start with this. How do I do the calculation? So you see that I can, here I have, everything is creation operators, but here I have annihilation, right? But I can reshuffle a lambda to here by using a commutator. So if I know the commutator, and this is something you're going to do in your homework, if you know the commutator, you can replace a dagger to the power a lambda by switching them plus the commutator, right? So, and then you get the commutator plus, by the way, what is this? Anybody knows? You're going to do it on your homework to prove a general formula. What is this? Okay, so it's actually, and this is for, sorry, I forgot. Of course, this is for the same lambda. If it was lambda prime, you get zero, right? But if it's for the same lambda, you're going to get, actually, it's like a derivative. It's going to give n lambda times a. lambda minus 1. Okay? Okay, so, and then, so this is, if you like, an auxiliary calculation. And then, so when I do the switch, once A is near the vacuum, it annihilates it, so it gives 0. And therefore, you can easily see that the result is n lambda, just here the number, not the operator, n lambda, the occupation, times n lambda. Okay? So the states with well-defined occupation of each quantum number are eigenstates of the number operator with eigenvalues, which are nothing but their occupation. Okay, so then now we can continue, and we see that if we now, I think a second less. So if we now apply n lambda of a particular lambda on a general Fock state, a general basis state of Fock space, not a general Fock state, okay, but a general basis state, what will I get?
And lambda times the...
Right, so of course, if none of the lambda i's here are equal to lambda, I'll get 0, right? But what I get, let's assume that here I'm summing over all possible lambdas, then I'm going to get just n lambda. So all the other states, I don't care, this operator doesn't care about them, right? It gives you 0. Because, why it gives you 0? Because if you apply, let me just mention it for completeness. If I apply this on a state where lambda prime is different from lambda, what will I get? I get 0. Why? Because then I can reshuffle the A lambda all the way to the vacuum without acquiring some finite commutator, and that will give me 0. And therefore, the only contribution I get from it is the occupation of the particular lambda I that is equal to lambda times the same thing, right? Okay, so the basis states that we chose, which are states with well-defined occupations of each quantum number lambda, are eigenstates of all operators, all number operators. Okay, okay, great. So now let's move forward to show that I can get exactly the same result if I now will write my O1 in this language. So, O1, I can write it as follows. O lambda, which is nothing but a number, it's the diagonal elements of the single particle matrix in the basis lambda. A lambda dagger, a lambda. Okay. Well, this is nothing but what we call the number operator. And so if you like, this is a definition, but when I apply it on any Fock state, I think you can easily convince yourself that you are going to recover exactly the same formula, right? Because what it will do, we already saw that the eigenvalues of n lambda of the n lambda hat, the eigenvalues are n lambda, right? So for each lambda, I'll get O lambda n lambda, and then I sum over all the lambda, and I get exactly the same thing. Okay? And therefore, I get all the possible matrix elements are well defined, and this is really an operator identity, because I proved that for arbitrary matrix element in my basis, I can write it in some way and it gives the correct matrix elements, then that's the answer. Okay? So, yeah, so this is going to give me some of the, okay, here the index I can just, it's just a dummy index. I can just call it lambda. I don't need the I, but this is what it will be. Okay, so the basis state of fog, because they have a well-defined number of particles in each state, if you express it, and again, it's important that we chose a representation where O1 is diagonal. Okay, that was the reason that we got something so simple. And then in the for assuming that little o, as I said, is diagonal in this. Okay, so I explicitly used this condition. Then I can write the single body operator in this form. Okay? But it's very particular to the basis lambda. Okay? And maybe we want to apply it on some state where there will be some different quantum number that will be more convenient or will be more relevant to the problem. But I still want to know what it will do. So this is not the most general way to write it. It's just a choice of basis that makes it simple. I can change to an arbitrary basis. And I know how to do it because we learned how to transform. I'll have to use these inner products or this unitary transformation, right? So, and then, so what I'm going to do now is, suppose I want to switch to some other basis, lambda twiddle. I rewrite A lambda and A lambda dagger in the other basis. Then you see each of these will give me a sum over indices that are independent, and therefore the final result will look like a sum over two indices, right? Generally, if the other basis is not necessarily diagonal, not simultaneously diagonal, then, okay, maybe I'll do it a little more carefully. So I can write A lambda as, here I'm just doing, let me write it as sum over, I call it mu, the other basis, whatever it is. And just to be careful, this is lambda mu A mu, and A lambda dagger I write as a sum over mu mu lambda, right? Yeah, that's right. Mu. Okay? Now the mu, let's assume that mu and mu belong to the same family of, it's the same basis, but it's a basis where the operator O, little o, is not diagonal. Okay? Then if we plug this into just plug this expansion into the diagonal form, I'm going to get the following result. Okay. So O1 is sum over mu and mu. There are two indices generally. Mu O, this little o, I'm trying to distinguish them, is acting on only single particle states. Okay, and this is a matrix element between mu and mu, which belong to the same set, but they are different in general from each other. Then I have a mu dagger. I did it in the right order. Just verify. Yes. Okay.
Shouldn't the DO thing like that?
No lambdas. So I actually. So what I did here. Let me define it. Okay. Let me define this matrix element. I didn't define it. So what is it? This is something that you can represent in terms of the O lambda as follows. What I do here, I put resolution of identity here and here. Okay, what is resolution of identity is the sum over lambda, lambda, lambda. Right? You know this, right? This is just a way to write the unit matrix in the basis lambda, right? It's sum over projections to all lambdas. It gives you 1. So I'm always allowed to stick it in between anything because it equals to 1. Okay, it's like the unit matrix. And similarly, I can plug it in here and write it as sum over lambda prime, lambda prime, lambda prime. Okay. And now, because this little o is diagonal in the lambda basis, I will get a delta of lambda and lambda prime, and the result will give me mu lambda, O lambda, lambda mu. Okay? All right? Okay, so that's a matrix element. It depends on 2 indices. All right? Sometimes you can always denote it a little if you don't like the bracket notation. It is conventional to write it as O mu nu. Okay, you can also write it like this. But in any way, it's a matrix element. Okay. Okay, so by the way, so what is actually the physical meaning of such an operator? where you notice that it's a summation over, generally it's a summation over processes where you annihilate the particle at state mu and recreate it in a different state. Okay? Let me give you a very concrete example where such things appear. Yes?
Can you explain why in the talk you don't sum over lambda? I mean lambda prime because you have a delta, but
Sorry. Sorry, I forgot the sum.
Okay.
Yes, sorry, of course. Yeah, of course you sum over all. Yeah, sorry. But you have only one sum because
yes,
of the
because
delta.
of the delta.
Yeah, sorry about that. Yes, you are completely right. Okay? Good. So, where was I? Yeah, so let me give you an example now of a case where I have an operator that is not expressed in the natural diagonal basis, but I have a very clear physical meaning to what it actually describes. So the example I want to give you is, let's assume that you have particles on a lattice, okay? And for simplicity, let's take a chain of atoms, like a one-dimensional Bravais lattice, and they have an index I and index J, okay? So these are now sites, and these are localized sites, or local atoms in the crystal, if you want. When I can write an operator of the form AI AJ W. What does it describe?
Only a particle moving from I to J.
From I to J, exactly. So this is what we call hopping. Okay, this is a hopping operator. Okay. And this is what it is. Okay, so this is IJ. I, and what will be the Hermitian conjugate of this? Just the opposite, right? Going from J to I, AJ, AI, okay? So where did we see such a Hamiltonian, that a single particle Hamiltonian that takes into account such processes? You've all seen it in solid state physics, right? And this is the tight binding model, which I hope all of you know what I'm talking about. The tight binding model for periodic crystals. You use a basis instead of using momentum states for the electrons. Let's say if there are electrons in a crystal, you are describing them in the basis of states that are localized on Bravais sites. These are called the Daniel functions. Just reminding the names, you don't have to remember, but generally such a Hamiltonian is written as, in the most general way, there is, first of all, there is a site energy that is diagonal. It's just a local energy on each atom, which in periodic crystals, it's actually uniform. Okay, so therefore you can just a number, a constant, plus, and this is where the hopping comes. in the tight binding approximation, you sum over nearest neighbors I and j, and here you have some hopping let me keep track of the order. Write it as AI dagger AJ plus its Hermitian conjugate. The Hermitian conjugate is TJI AJ dagger A. Okay? And in many simple models for crystals, we choose the T, which depends on the distance between particles, will be a constant again, just one parameter T, right? You're familiar with this? Okay, so this is an example. Now, for periodic crystals, as I said, epsilon I is just epsilon, and Tij is just a constant.
Why is it minus?
That's okay. It's a convention that gives you a lowering of the energy. So, okay, T, of course, can be, in general, a complex number. You can have a phrase. But the convention is to choose it in such a way that if T is positive, it lowers the energy. Okay, the hopping lowers the energy. Okay? But it's just a convention. Okay? It's generally a complex number. Okay? Therefore, the minus sign doesn't have much meaning, but unless if you have two types of hoppings that compete with each other, one is positive and one is negative, then it matters a lot. It's the relative phase. Okay? But in any case, the most standard, simple, tight binding model is that you have just one epsilon here, which doesn't play any role because it's like a constant, right? And then you have, and then this is a constant too. And because of the periodicity, you know actually how to diagonalize the Hamiltonian, right? What is the basis, or what are the eigenstates that really diagonalize this Hamiltonian? They are Bloch waves, right? For periodic crystal. And then the index is a quasi-momentum and not a site index. But you can write it in this way and switch to K-space and get the diagonal form. Okay? But we'll see soon that if you want to introduce interactions in a crystal, the interactions are usually local and they are much simpler described in the basis of the site and not the basis of K-state. Okay? And therefore, that's why I do want to remember how it looks. But the meaning of this is just, as we said, it's a hopping. Okay? And if it's something off diagonal in K-space, you annihilate a K and create K prime. What does it describe? That's a scattering process. Okay? Where you change the momentum from K to K. Okay? All right. Good. So let me give you a simple, one of the most simple examples of a single particle operator. So, or a one body operator is let's erase this, which again is conveniently written in its natural diagonal basis, is the number operator, total number. N, what is it? How can you write it? In general, if you have, so it's an operator that counts all the particles in the system in an arbitrary Fock state. So you can write it as a sum over n little n lambda, where now here the sum is over all lambdas. Okay. Now you can apply it on a state where only a few lambdas are occupied. And that's fine, but if you want an operator to describe all the possible Fock states, then this is it. And changing a basis from lambda to R, you can actually prove that the change of basis keeps it diagonal, in a sense, because so you can convert from one set of quantum numbers, but you sum over all the quantum numbers, right? So if you change basis, and you will just counting particles, you don't care what the quantum number describes, that's all the information, then it doesn't matter in what basis you write it, it will always be the sum over all the quantum numbers in this set times n. And in particular, you can write it in real space, in terms of local operators. But real space R is not a discrete variable, it's a continuous variable. So how will it look in real space? It will be an integral over R of the analog of the n lambda, but now it will be n of R, but it's now written in terms of, so notice n lambda is A dagger A. What I'm going to put here is the density operator, where density operator is okay. All right. So and actually you can of course relate these to classical quantities, because if you have a state that is an eigenstate of the density operator, its eigenvalue is going to be just the density, the local density, and the integral of the space of the density give you a number. Okay? So this is an example. But one caution I want to make here is that when I'm writing the density operator in this form, I'm assuming that the particles I'm talking about are fully described in terms of the local coordinate. And you know that it's actually not true. For example, for electrons. Why? Electrons are particles that have another degree of freedom that cannot be described in real space. What is it? That's a spin. Okay? So, more generally, for particles with a spin, or it doesn't have to be a spin, it can be some other internal degree of freedom, like a pseudo spin of some sort, and you can define, so let me write it here, for particles with a spin. So I can define psi and psi sigma. Okay? Creation and annihilation, what do they describe? They describe the creation or annihilation of a particle with spin sigma at point R. Okay? And then the density operator of such particles if I want to describe the density of particles at a point R, I have to account for the possibility that I can also, at the same R, I can use different sigmas, right? So it's actually a sum over sigma of psi psi, psi dagger psi. Okay, so that's important to keep in mind, and it's true for any internal degree of freedom. We'll give you another index generally. There's one thing that I forgot to mention, and just let me now say it for completeness. When I'm changing a basis from lambda to some lambda twiddle, from real space to k space or whatever, what happens to the commutators? So we know that these A lambda dagger have to obey the commutators or anti-commutators. They have to obey this algebra. What happens when I do a unitary transformation? They have to stay, they have to maintain the transformation from one basis to another have to obey, the resulting operators must obey the same rules in the new basis. Okay? That's very important. Otherwise, it's not a legitimate basis transformation. Okay? Now, with regards to these operators, the psi of R, because they have non-trivial units, the R is a continuous variable. So I remind you that the commutators, let's talk about commutators without how to say without keeping general terms. I mean, it's true also for anti-commutators. So this is the commutators of a discrete index. But if I'm looking at the commutator or anti-commutator of psi of sigma of R and psi sigma prime of R prime, what will be the right-hand side? Now it's going again to be some delta, but it has units. It has units because psi has units. Psi goes like 1 over square root of the volume. So psi has units of 1 over basically units of density, 1 over volume. So this is going to be a delta of sigma prime. This is still the usual, but this will now become the Dirac delta instead of a commutator. That's all. Okay, and the same is true for the anti-commutators if they are Fermats. Okay. All right. So that's all I have to say about one-body operators. And if we have only one-body operators, it's not clear that we really need the second quantization because we already know how to deal with it, right? Because all we need to do is to diagonalize the Hamiltonian for a single particle, and then you can throw as many particles as you like in it, and do statistical physics if you like, and everything is simple. So what we're really interested to learn about treating in this course is interactions. So the next thing we'll introduce is a two-body operator, and you already see, let me say last thing about the one body operator before we switch. So in a one body operator, you acted each time on just one particle. Each term in the sum, although it has two indices in general, it acts only on one particle. It may change its state, but it annihilates and creates it, okay, or scatters it from one to another. A two-body is going to be something that acts on two particles and does something to them. So before I start writing, what do you guess will be its form? How it will look? What will be the formula? It's going to be some combination of A and A daggers. How many operators do I need?
Four.
Right?
A dagger A is different.
Exactly. So the most general, so this is already a guess. It will be, it will have a sum over 4 indices in general, and it will include 2 annihilation and 2 creation. Actually, these are even this and the two-body operator that I'm going to introduce soon are not even the most general type of one-body or two-body operators that I can think about, because notice that one thing we can say about O1 is that it maintains the number of, it doesn't change the number of particles, because it destroys the particle but then creates it again in a different state. So the total number of particles is not changing. But there can be operators that reduce or increase the number of particles. They are legitimate operators. They, in fact, we're going to see later in the course cases where the Hamiltonian may include such operators. And therefore, its ground state and its eigenstates in general will not be Fock states, because Fock states have well-defined number of particles, right? So there can be more general operators that you can still, in a sense, call one body, although it's not really it's not really well-defined in terms of number of particles that are AA or A dagger, but and similarly for higher order. But for the ones that conserve number, the two-body will have 2 annihilation, 2 creation. 3-body will have 3 annihilation, 3, okay, 6 altogether, and so on. Okay, so let's start talking about 2-bodies, and we'll give some examples. Okay, so the most common, the most I don't know, abundant or useful two-body operator originates from the case that you have some interaction between particles, between 2 point particles, like the Coulomb interaction. Okay, so in terms of the first quantization, or actually, if you like, let's go back to classical physics. Okay, you can have some force that comes from a potential acting between 2 point particles. Okay, now in a many-body system, and still maintaining the classical description, how will you write the interaction that takes into account the fact that you have many particles, but they may be distributed in space in different positions? you then have to integrate over density, over all the coordinates of the two particles. So you have some potential that depends on R1 and R2, okay, and that's like the basic. So here you have some R1, there's another particle located in R2, and you have some force acting between them, and there's a potential energy associated with them, and we call it V of R1 and R2. Okay? And most interactions that we are familiar with are in fact symmetric, right? They don't depend. I can exchange R1 and R2. So we want to restrict ourselves to such interactions. They only depend they depend symmetrically on the two coordinates. They're mutual. And in the more special case, but quite common, we actually want to assume that it depends only on the distance, not on the direction. It's not always true, because, for example, the interaction between two dipoles, the electric interaction between two dipoles depends also on the direction, okay, of the relative coordinate. But in Coulomb interaction between point charges depends only on the distance and so on, okay? All right, so, but let's just leave it like this for the general case. So, in classical physics, I can write the total, what will be the total potential energy of the system coming from this interaction. It will be an integral over R1, integral over R2. You notice that here I'm keeping the dimension arbitrarily, okay? The dimension of the system. And the integral may be on some finite volume or infinity, doesn't matter. And then I have, let me write it in a symmetric form. I have rho of R1, V of R1, R2. It's the interaction, and then rho of R2. Okay, so it's the product of density times the potential. Okay? This is, for example, the total Coulomb interaction of a set of charges that is characterized by some charge density is just let me just write it here for Coulomb. Oh no, sorry. This is actually a special case that is very relevant, because that's the interaction between electrons in a material. Then V is given by E square. Okay, this is between electrons. Otherwise, there's some other Q, Qi, Q1, Q2. What? It's just the Coulomb interaction. Okay?
So
Yeah?
you count twice which is the dimension.
Thanks for the comment. Actually, there are two corrections I want to make. First, I put a factor of half here, exactly for the reason that you say, to avoid double counting. Additionally, I want to put a prime on this, which denotes that I don't, so R1 is different from R2. So you integrate over all the R2s that are different from R1. Okay? Why do you want to avoid the same point? Because, for example, if it's a Coulomb interaction, it will give you a singularity. Okay? It's not always the case, but sometimes it's better to write it like this, although we'll see a case for interactions on the lattice where you do allow such things. For the Coulomb interaction, you definitely want to exclude the point, the self-potential energy. Good. Now, what I wrote here is classical, right? But I can easily turn it to quantum. How? Exactly. I put a hat here. And here, where do I have to put my hats? Right, okay? Actually, V of R1, R2 is just a function. Okay? It's, for example, this function. Okay? So the operator is actually embedded, the operator entity is embedded in the densities. And now, so by the way, this general form is called density-density interaction. But you can, and usually this is the basic microscopic interaction between elementary particles is density-density, but you have already seen there are interactions that are cannot be written as density-density, but they still exist. For example, if you have charged particles and you have local currents, there is a current-current interaction, right? In the Hamiltonian of charged particles, if they're moving in a conductor, you can have a term that is a current-current interaction. How is it called? What is the physical significance? It's like an inductance, right? Inductance is, okay, the simple case is just I square over L, right? Or, so Li square, right? The L is the inductance. Remember that, right? Hashraut. Inductance is hashraut. Okay, if you don't remember. So the magnetic energy of two wires carrying current is proportional to the product of their currents, not their density. Okay. And there are other forms of interactions, but usually they are emergent from something that the more basic thing is that, like spin-spin interaction, okay, like Heisenberg model. And then this, so you will see, you will discuss, I think maybe in the tutorial of next week, some other examples of that, but the general form is very similar, except that instead of the densities, you're going to put currents, and then because, or spins, and because these are vectors, it's going to be a scalar product, okay? But it still has the same form of a one-body operator. So remember, rho was a one-body operator, and so is the spin. So it's some one-body operator times another one-body operator, and you sum over some quantum number. In this case, it's the location or the coordinate. Okay, that's how it looks in real space. But and let us now let us now do one more step, and then we'll take a break. what is the density operator? Now I want to express it in terms of creation and annihilation operators. And that will already give me an expression for such interaction in real space, in the real space basis. So we recall that rho is, let me be more general and put a spin index here, which might be just 1, or plus 1 and minus half. Okay, can be some internal degree of freedom. Okay, but it's diagonal. It's diagonal in R. And now I plug it here, but here I have R1 and R2. I have 2 coordinates. So when I plug this in, let me write a general expression. I get a sum over sigma prime, an integral over R1, an integral over R2. And now I'm putting, let me write here the potential, because it's just a function of R. It's not an operator. I'm allowed to commute it and put it here. Okay, that's what I have to do. And then I'm plugging in my densities, but notice that I want to write it in a bit of a funny form. Let me be very careful. So this is R1. And now R2. So what did I do here? Notice that if I just plug in the expression for each density, I get a psi dagger psi, psi dagger psi. What I did here, and actually this is not, this thing is equal to that only up to some constant. Okay, some or some, maybe not a constant, some single body. So there's no direct equality between this and this, because I'm missing here something, but the other something is not going to be a two-body operator. And what did I do here? I reshuffled the annihilation operator psi to the right-hand side. Okay? And by the way, notice that it doesn't matter if these are fermions or bosons. If I reshuffle an even number of times, I get a positive sign. Okay?
You forgot again the half and the half.
What?
You forgot the half.
Yeah, I forgot the half, right, and yeah. Okay. That's right. So keep reminding me, because for good measure, I don't know. Okay. Now, why did I want to write it in this form? And we'll discuss it much more in later classes. But this is this way of writing an interaction is called normal order. And what is its advantage? If you take such an operator and apply it on the vacuum, what do you get? 0. Okay? So therefore, the vacuum expectation value of this is 0. Okay. Now, of course, this is 0. Now, you may say, I mean, this looks trivial, right? But it's actually not really trivial because, as we already discussed, the definition of a vacuum is a biased choice. It's not, there's no universal vacuum. I mean, there may be something like that for the universe. But for our purposes, a vacuum is something we want to keep dependent on a problem. And, but you always want to define your interactions, and actually all the terms in your Hamiltonian, in such a way that the vacuum expectation value is 0. Otherwise, you have to keep track of a 0-point energy, which usually doesn't have a physical meaning, okay, or a way to measure it, okay? So, so this is the way we write it, and I think now let's take a break and convene again at 6, and I'll show you how to go to different bases. Let us now write, so this form is a general way of writing a density interaction in real space, but sometimes it is more useful to switch to a different basis, just because, for example, the single particle states are better described in momentum space or in some kind of other quantum number. So using this mapping or unitary transformation from one basis to another, it is possible to express the local operator Saldegger as a sum over lambda, and here we write phi lambda of R of A lambda Dagger, and similarly for psi. Okay? So, and now in our expression for the two-body, we have 4 field operators, psi, Dagger, each with their coordinate. Let me actually assume that lambda is most general, and in fact it includes the spin, although the spin, because it's a different degree of freedom, I'm not allowed to write an electron actually in a point R as a sum of spin up and spin down. It's not correct for like the spin of an electron, for example. But just for keeping the notations simple, let's assume that the lambda includes all the quantum numbers that okay? So I can use this transformation for the 4 operators. Each of them will have a sum over some other dummy index, lambda prime, mu prime, let's call them. And after you plug it in, and I'm not doing the algebra, but it's straightforward, you find that a more general representation of V is the following. You sum over 4 indices, which I call mu prime, lambda prime. They're all taken from the same set. Then there is a matrix element that I write like this, and And actually what I'm writing is true for any two-body operator, so I can equally replace this notation by O2, but I'm thinking of the density operator in particular. And then you have 4 operators. Okay, and please notice the order of the indices, which keeps track of the fact that the lambda and the mu are actually starting from the same density operator, but I reshuffled it here. Okay, so this is just the most standard way of writing it. Now, what is the matrix element? O mu prime lambda prime. Here I'm writing a definition. So it is, if I'm using a bracket notation, it's it's a matrix element between two particle states. Okay, lambda lambda prime and mu mu prime. And more explicitly, in terms of coordinates, you can write it as an integral over r and r prime of let me write it like this. So it's phi mu r, phi star mu prime r prime, v of, or if you like, O, let me just call it O2, not V. I want to be very general. But this is nothing but a potential that depends on the 2 coordinates. And then I have phi lambda prime r prime, phi lambda of r. Okay? So this is an explicit integral. Okay, these are wave functions, and in principle it allows you to calculate. It's a matrix element of the interaction, and it's just a number. Okay, and generally it's a complex number, right? But of course, if it appears in the Hamiltonian, it must be, because the interaction is a Hermitian operator, like any physical operator, then you should have the sum of terms that give you something that is Hermitian conjugate. Okay, every term comes with its Hermitian conjugate. Okay, so this is the most general way of writing a two-body interaction. Let me put it in a box. Change the notation. Okay, and that's the definition. And now we are going to give an example. And actually, when I'm writing it like this, since I'm allowing the indices lambda to include both spin and momentum or whatever you like, this kind of expression describes also not only density-density interactions, but also spin-spin and current or any other kind of interactions. All of them are captured by something that has 4 operators, 2 annihilation and 2 creation, and it's just a sum over scattering processes in a sense. Okay, scattering in the whatever basis you're writing it. If the lambda and mu are lattice sites, what it can describe is combined hopping processes, where you take 2 particles from 2 states and shuffle them. Okay, or if it's in K-space, it describes scattering, really, that you have 2 incoming particles with some momentum and 2 outgoing particles with another momentum. Okay? So, and actually this is a concrete example that I'm going to discuss soon, because if we're talking about interactions like quantum interactions, which are dependent, where the interaction potential depends only on the difference between R1 and R2, and the system is homogeneous, so there is translation invariance. The center of mass momentum is a good quantum number, right? And then even if you have scattering between particles, the total momentum has to be conserved. So that is actually a constraint that simplifies the expression in K-space. Okay, and we'll get to it. Just a notation that is going to be very useful. So I can now erase all this. Yeah, so I can represent each term in the sum. Here I have a sum over many processes, and as I said, it's a process where you annihilate 2 particles at lambda and lambda prime, and recreate them at mu and mu prime. And the amplitude for such a process is described by this matrix element. So I can describe it schematically by a diagram where there are incoming particles at lambda and lambda prime. Here there is some junction where something happens. There is a matrix element that couples states with different quantum numbers, and this is represented by the matrix element O. And then I have 2 outgoing at mu and mu prime. Okay? Now don't care. I don't care about the direction of the arrows. So since lambda is not necessarily momentum or anything like that. It is just a schematic diagram. So the interaction, so the direction is not important. What is important is the graphic symbol that there is a junction that connects 2 annihilation and 2 creation operators. Okay. Now, why do I need this? Of course, you can just write the expression. You don't necessarily need a graphic language. When do you need a graphic language? When you want to account for complicated processes where you apply the interaction again and again. Okay, like for example, we'll see later that you can sometimes you can do perturbation theory on the interaction, because usually you cannot solve a problem with interaction exactly. Okay, there are very few, very special models where you can map interacting problems to some free particle emergent description. In fact, we did see such an example in our first classes in this course, but generally it's a hard problem, and there are various tricks how to treat the interaction. One of them, most straightforward, is if the interactions are weak, we can do perturbation theory, right? But in perturbation theory, if you go to higher order, you are applying this operator not once but twice, okay? And then, or maybe even infinite times, and then the graphic language, by translating it to a diagram, you can see what's going on and even do the calculation in a compact way, okay? And I hope I'll get to show you an example of this, all right? Okay, so this was very general. Now let us take a concrete example. Which is okay. Or in fact, you can think of it as interacting fermions in general. But let us focus on electrons, because there is a spin index, and okay, and it's a very relevant problem to look at electrons in solids as an example for a case where to describe many phenomena, you have to deal with the interactions. The interactions are not small. Why? Because electrons are charged, okay? And although in some materials like metals, we learned in our undergraduate that you can treat them as a free fermion gas because the kinetic energy is very large. That's true, but still, if you just naively look at the energy scale of the Coulomb interaction compared to the kinetic, which is Fermi energy, you discover that in fact they are of order, the ratio is of order 1. It's not small, okay? Coulomb interaction is very, very strong. So there is a sophisticated reason why in some cases we can neglect it or treat it perturbatively. But it does exist, you cannot ignore it, okay? And there are, of course, many other examples of, and in fact, except maybe for photons, in a vacuum or in a linear material, most problems of many particles involve interactions. Okay, so yeah, so let me write Hamiltonian that has the following terms. It's there's a single body part which I call H naught plus interaction. And the single body part in the first stage, I'm going to focus on a situation where there is some external potential, so it's not necessarily free particles, free electrons. But there is some potential, and in principle we know how to diagonalize the single body part. Okay, so let me first write it in a more most general way. We can write it as integral over coordinates of and there is also a spin and the sum over sigma of psi sigma dagger r times, and here I have p squared over 2m plus some potential. This is the external potential, which is acting locally on all electrons, and psi sigma. Okay. This is the most general single body term. And here, psi sigma r and psi dagger sigma r, they are describing annihilation and creation of an electron with spin sigma at point r. Okay? And here, by the way, when I write this expression, what is P? Which appears inside, all of this appears as an integral over R. So I want to write the momentum operator in real space. How do I write it? It's actually a vector. What is it?
H bar.
Exactly. Okay. Right, so this is the usual Schrödinger equation, if you like, but here psi's are field operators. Okay, second quantization. Okay, so this is what it is, but I told you let's take a potential that we know how to solve, and we have some quantum numbers lambda. In particular, if v is 0, the quantum number is going to be just the momentum, right? Or wave vector k. So it is convenient to write it in, yeah?
The Hamiltonian includes both H naught and the
Sorry. This is just H naught. Sorry. Yeah, we didn't get the interaction. You see, it's a single body. It's a single body. Sorry. Yes. Thank you. So I want to rewrite it as in the basis that is more convenient, and notice that it will be convenient only for H naught. Of course, in the interaction, I can't get away from the fact that I will get this form with all the indices. Maybe the matrix elements will be such that I will get 0 if the lambdas are very different. Or okay, I have some matrix elements that are 0, or I have some rules that relate to them. We'll see an example for that, but generally it will be complicated. It will have this form, and we have to calculate what are the matrix elements. Now, but the H naught will have a much simpler form, which is, I can write it most generally like this. Okay, and the epsilons, what are they? They are the eigenvalues of this single particle Hamiltonian. In other words, they are the solution of the single particle Schrödinger equation. Okay? I can even write it, so if I call this, let's call it H naught operator, then I have some wave functions that are this, phi of lambda. Okay, here phi are functions, okay, they are the wave functions of an electron at state lambda with spin sigma. Okay? Okay. Good. Okay, so I have a simple expression, a diagonal expression for the H naught. What about V? V will have this general form. Okay? Well, here the lambdas and the mu's are taken from the same pool, the same set of quantum numbers. So I cannot simplify this further, but I can do it for special cases. Okay? Let's see what special cases we might be interested, at least as the most, it's the simplest case we can think of. What is the simplest potential we can choose here? 0, right? So let's talk about free electrons. Well, when I say free, it's only the H naught that is free. Okay? Okay, so erase all this. Okay, so V of R is 0. That's the case where we have the free electrons. So the lambdas are in fact K vectors, eigenstates of the momentum. And you just have kinetic energy, and H naught can be written as a sum over K and sigma, epsilon K sigma AK sigma AK sigma. Okay? What are AK sigma? They are operators that create electrons at momentum K and spin sigma. Okay? Well, epsilon K is for free electrons. What is it? Just usual kinetic energy. H bar K is the momentum, the eigenvalue of the momentum. And actually, in a more generally, this form is correct also not only when V is 0, but also when V is periodic potential. Then, of course, momentum will no longer be a good quantum number, but instead we will have the eigenstates are Bloch functions, okay, and the quasi-momentum is going to be a good quantum number. And the epsilon of K will not have this simple parabolic form. It will be some bent structure, but it will still depend on only one index, on the K. And notice that there's actually, I wrote here epsilon of K and sigma, and there's no dependence on the spin. But there can be, for example, if I put a magnetic field that couples to the spin of the electron, I can get corrections. I can get a Zeeman effect. You remember, right? There is a S dot B term. So there will be some shift of the states that depend on sigma, but let's forget about it for a minute. And it doesn't matter because in either way, I can write it in a basis where it's diagonal. Okay, then of course I will also have to choose a basis that is diagonal in the spin, right? And usually we define the z-axis in the direction of the magnetic field or something like that. Okay, so that's the free part. And if we didn't have interactions, we also know what are the states of the general state is a Fock state, and because the electrons are fermions, what can we say about the occupation? The occupation.
Only principal.
Yeah, so it cannot be more than one. Okay, so in particular, what is going to be the ground state? So we have, let me assume now that we have, this is the spectrum of electrons, and I have, if I have a fixed number of particles, then at the ground state, which is the zero temperature state, is going to be the lowest energy possible for fermions. What is it? It is a state where I start occupying the lower level, and because I cannot put more than one or more than two, if you have a spin degeneracy, then I'm filling all the levels up to some level that depends on the density or on the number of particles, right? So alternatively, I can assume that there is a chemical potential, and this defines a so-called Fermi energy. And all the states below, this is at zero temperature, of course, the ground state, which I'm writing like this for Fermi C, is going to be a state where I occupy once all the states with energy up to E Fermi. Okay? So how do I write it? I write it as a product over lambda. Let's not think about the K necessarily. I want to write something more general, but of course it applies also when lambda is K. So every lambda where epsilon lambda is bounded by the Fermi energy is occupied once, and all that is acting on the vacuum, right? Okay. Okay. So that's the ground state. The ground state of H naught. It is not necessarily the ground state of the interacting system, okay? But it's the ground state of H naught, and if the interactions are small, and we want to do perturbation theory, then we can use it as a reference state on which we calculate the matrix elements of the interactions that give us the perturbation theory, right? You remember how you do perturbation theory. To first order, you take just the expectation value of the perturbation. Second order, you have to sum over matrix elements with a denominator. Okay, you have some expansion, but this is the state that you're going to use as your reference state for doing perturbation theory, okay? Okay, great. So now let us focus specifically on the case where the potential is zero and the electrons don't see an external potential that affects their wave function. So the entire space is homogeneous, right? There is, in other words, translational invariance, and the interaction, which is Coulomb basically, is a mutual interaction that depends only on the distance between the two particles, not on the total shift in space, right? So this is a case where using a momentum basis is expected to be most useful. So now let me write the interaction. So this is, I'm just reminding that H is H naught plus V E, and now I'm writing V E. And to start with, I write it as a density-density interaction that we had before. So it's integral over two coordinates. I call them R and R prime. And here we have I mean, of course, I can write these density operators in terms of the fields, but at the moment I avoid it. You'll see in a minute why. And then I have an interaction, and the interaction potential is a function of the difference. Okay, depends only on the difference of R and R prime. So let me write it like this. And just for a side, I remind you that I can write the density operator as a sum over spin of psi dagger R psi R of the same spin, okay? And I can, when I plug this in, I can do normal ordering, but at the moment I just leave it like this. It is correct. And why do I leave it like this? Because I think you see that I can, now what I would like to do is to go to Fourier space, because I see that my good quantum numbers are k vectors and not coordinates, right? So I want to do a Fourier transform on all my operators such that at the end I will have the interaction expressed in terms of a sum over k vectors. But notice that we know that we have here a symmetry in our problem, because the potential energy, which is the interaction, depends only on the distance. The system is translationally invariant, and the center of mass coordinate, so the translation invariant of the center of mass coordinate. So there is at least one momentum that has to be conserved, and that's the center of mass momentum, right? So we can allow, the interaction can force electrons to scatter. They can change their momenta, but in such a way that the total momentum will be conserved. Now, mathematically, how do I see it? You see that, let's look at this integral, okay? And I want to rewrite it a little differently. So let me leave here, there's a row of R. Okay, because this does not depend on R prime. And the integral over R prime, I leave separately. And I want first to integrate over R prime. Now, what do I have here? You agree with me that this this integral has the form that I have a product of a function at R prime and a function at R minus R prime, and then you integrate over R prime. How do you call this kind? A what?
Convolution.
That's a convolution, exactly. And you know that as a Fourier transform of a convolution is just a product, right? So, using this fact, you can easily convince yourself that I can rewrite the interaction in the following way. So sum over Q, Q vector of, let me leave here the VEE Q. I'll define it in a minute. And then we have rho Q. And this is something I have to okay, let me yeah. Let me write it like this. Okay. Well, now I have to, I'm owing you some definitions. So first of all, what is VEE of Q? It's simply the Fourier transform of here. So VEE of Q is okay, and here we might, it's a matter of definition, but let's introduce a normalization factor of 1 over volume of the Fourier transform of V of R this is what it is. Just a Fourier transform of V of R, where V of R is, so remember in this expression I have a V of the difference, R minus R, but it's really a function of a single variable. Okay? So it's a single variable, and so for example, for Coulomb interactions, this is E squared over R. Okay? By the way, what is the Fourier transform of this in 3 dimensions? You know? Did you ever see it? What is the Fourier transform of E squared over R? For D equals 3, because it depends on dimensionality. No? Okay. I don't know if you've seen it ever, but actually it's relatively easy to calculate using spherical coordinates, and you get that it's 4 pi E squared over Q squared. Okay? Yeah. Okay, but this is really a special case. But and if yeah, and if there is yeah, okay, we'll discuss later some other forms of interactions, but this is the basic form of interaction. Now, what is rho? So all the quantities here are Fourier transforms of what I have in the original expression, and here rho of Q is, first of all, definition. What is it? Again, a Fourier transform of the, and it's an operator, sorry, I forgot to put the hat. Everything here is an operator. It's, up to normalization, it's the Fourier transform of the density operator. And, however, you can, because you can express the density operators in terms of the field operators psi r, psi of r and psi dagger, I can express, I can plug this in, I can rewrite it here, and then I can convert psi and psi dagger to a k to the let me write here the transformation. Psi dagger of r is a sum over k. This is the Fourier decomposition of a dagger k sigma e to the, because it's a dagger, it's minus k. Okay? This is the Fourier components of the operator psi dagger, and for psi you have the same thing but with plus here and a. Okay? So so there is something that you are going to do in your homework, showing that if you use this definition and the expansion of the field operators in terms of A and A daggers, you can show that the density operator can be expressed as a sum over k and sigma of a dagger of k minus q sigma a k sigma. Okay? Okay, that's okay. That stage is homework exercise that will appear in homework number 3 or 2, I don't remember, but will appear. Okay, it's just straightforward. So if you open this, and there's another important thing I want to note. So notice that in real space, sorry that these are this distance from each other. In real space, the density operator is local. It's diagonal because it's at a point r. Right? In momentum space, it's not. Okay, it's a single body operator that if you write it in the wrong basis, and for density operator, the natural basis is local. But in momentum space, first of all, there's a summation of many momenta. Okay, and what is the significance of this expression? It is diagonal, of course, in the spin. The spin we didn't touch, but it's a summation over all processes where you annihilate an electron at momentum k, and change it to k minus q. Okay, so there is a momentum transfer, momentum change, and that momentum is exactly the q. Okay, that's the meaning of it. But for the same q, k can be anything. So here you sum over all possible k. Okay, so it's an operator that in k space, what it does, it takes it's a hopping process in k space, right? It takes an electron with some momentum and transfer it to another momentum. And it has an interesting symmetry. Notice that rho of r, the local density, is it's really a physical operator, right? It's density, something that we can measure. Can calculate its expectation value. It has it's a meaningful physical measurable quantity. What do we know about physically measurable quantities? The operator that describes them must be Hermitian. So rho of r is Hermitian, but rho of q is not. How do I see that it's not Hermitian? Because when I put a dagger, the dagger also changes the sign of, there's an I here, right? So the q component of rho is not a Hermitian operator. And in fact it has, there's a general property that we already used, if you remember in our earlier lectures with the phonons. When you have an operator or a field, or it doesn't matter, even if it's a classical field, that is Hermitian in real space, in momentum space, the Fourier components obey that the dagger of rho q is rho of minus q. Okay? So rho q dagger is just rho of minus q. Exactly for the same reason that we've seen the operators phi and pi of the momentum and coordinate were. And therefore, when I write this expression, I can re-express it as sum over q of VEE of q, and then I have rho q, rho minus q. Okay? Actually, you see here I also switch the q and minus q, but it doesn't matter. Why am I allowed to do it? Because I'm summing over all q. So every q has a minus q. That's included in the sum, and also, of course, rho of q and rho minus q are commuting. Okay? So, yeah, okay, actually, okay, we have to be careful. They're not exactly commuting. They're not commuting, sorry. They're not commuting, right? But the commutator is a single body operator, and that's exactly the story with the normal ordering that I mentioned before. So if you rewrite them in terms of the A's and A dagger, up to some correction that has a vacuum expectation value, and we're not interested, we're going to get something that has four fermion operators in it. So let me now write it more explicitly. Where should I do it? Okay, let me erase this. Actually, let me just for not to confuse, I write it again. Sum over Q of V of Q, rho Q, rho of minus Q. And then if I'm using the expansion of rho of Q in terms of the fermions, I see that the expression I will get is 1/2, and now I will have a sum over. Notice that here I have a Q and the minus Q. So the sum, here the sum is only over Q. But each of these is a sum over K. So how many indices I have to sum over? K, K prime, and Q. 3. Why not 4? Because the total momentum is conserved. Okay? So let me write down what we eventually get. So there's a summation over 3 momentum indices, K, K prime, and Q. And also we have 2 distinct spin operators, right? Because each density has a summation over spin. And inside the sum, first of all, we have the Fourier transform of the interaction at momentum Q. And if I write it in the normal order, and I'm writing it like this, let me just define here on the side, for any operator, it's a normal order of O, of the operator O. What do I mean by normal order? It's a form where all the annihilation operators are on the right-hand side. So it will not have a vacuum expectation value. Okay? Okay, so now I'm writing it. How does it look like? It's A dagger K prime sigma prime sorry, A dagger of K prime plus Q sigma prime, and then A K prime sigma prime, A K sigma. Okay? Good? Okay. I mean, you can do the algebra yourself to see that it comes out, but this is actually very interesting because I now want to convert to a graphic language and draw a diagram that describes each term in the sum. So here we have a sum over many indices, and each inside the sum you have some process, some scattering process. Okay, and you see that the scattering process is in fact, yes?
Is it K sigma, K tag sigma tag on the annihilation?
Yeah, sorry. I forgot the problem. Yeah. Thank you. Right? You see that you are still alert. That's good. Right? So you see that the momentum, total momentum is conserved in every such process because I annihilate electrons with momentum K and K prime, and then there is a momentum transfer to K prime. I add momentum, sorry, I forgot the vector sign. I add momentum Q to K, I reduce the same momentum so that the total momentum of the particles will be conserved. Okay? And that has to do with the fact that the center of mass momentum is conserved. Okay, so let's draw a diagram that describes this process. And later we see that we use this diagram very economically to get a lot of physics. And the diagram here has an interesting ingredient in it. So what is it doing? There is, first of all, there is this describes a particle with spin sigma and momentum k. There's an incoming particle that I also destroy with momentum k prime and spin sigma prime. And here there is the following thing happens. There is some line that carries those. It's like a particle that actually, let me draw it not like a spring. It's not a standard notation, but as a wiggly line. Okay, there's a wiggly line. This wiggly line describes the propagation of a particle with momentum q, and this, you can imagine it to be something that the electron emits, and it carries with it a momentum q, which it transfers to the other electrons. So now after the scattering, you create, and this describes now, so these are the annihilations, k prime, and after the scattering, I get k minus q, and sigma stays the same, and here I get k prime plus q, and sigma stays the same. Okay? Yes?
But in which Hilbert space this particle lives now? Because now it does not exist.
Right, so this particle is outside our Hilbert space, you are right. In fact, this is, if you like, just to draw the diagram, I described it as something that represents this function. Okay, for us, this is just a function. It's actually a number. It's not, this is not an operator. Okay, I should stress it. It's not an operator. It is a function of Q. But it's a function of Q that I'm claiming that it describes an expectation value of some operator. And what will be this operator? It will be, and it is in fact, the number operator of a particle that carries the interaction. So, or more generally, we call it a gauge particle. In the particular case of the Coulomb interaction, what is this particle? Just a guess. It's a photon. Okay? So this photon, where did it come from? It's not there, right? But we're talking now about field theory. Particles can be created from the vacuum if they have the correct conservation laws. And a particle, when a particle is annihilated and recreated with a different momentum, it is allowed if it ejects the extra momentum as some particle that carries the energy and momentum. Okay, so it has to conserve energy and momentum. And this photon, so in fact you can imagine the mutual interaction between two charged particles as a second order process where actually each particle, one emits a photon or a gauge particle and the other receives it. So the gauge particle, which usually is a boson, usually, okay? It doesn't have to be, but in the most standard example it is, and it's called a gauge boson. It's kind of an intermediate mediator. It's a mediator, okay? So when two fermions or two electrons are interacting via Coulomb interactions, they are exchanging photons, and these photons are virtual. They are emitted and immediately, you don't see them, right? You don't actually measure them because they're just immediately emitted in a sense. But that's what happens, okay? That's a microscopic description of the process. Yeah?
I have another question. If the Coulomb force will continue, we know that the force is 1 over r. So the electron does not diverge, I mean, in energy? Because it will continue and continue?
No. Actually, you know, the fact that, this form that I claim that this is something that is beyond today's class at least. I don't know if we'll get to it. But I'm claiming that what I've written here, which has the 1 over q squared, is in fact can be identified with an expectation value of, let me call it B dagger B, where B is B and B dagger are creation and annihilation of a photon with momentum q. And the fact that it goes like 1 over q squared and doesn't have q squared plus something is a signature that it's a particle that has no gap, no mass. Okay? If it had a mass, the Fourier transform would have an exponential decay. And we'll see, we'll get to it later. Okay? So the properties of the mediator determine the space dependence of the force, and the force or an interaction that goes like a power law is a signature of a massless particle. Okay? Okay, in terms of the gauge boson that carries it, if you look at the other gauge bosons that we have, like I don't know, gluons and and the carriers of the weak interactions and so on. If they have, because the weak interaction is a good example, the gauge bosons have a mass, therefore the interaction is short range. It's decaying faster than power. Okay. Okay, so but that's I'm jumping a little ahead. Sorry, but I hope that we'll get to it in the last lectures, one of the last lectures. Okay. But in any case, I mean, just looking at this expression, it's very easy to convert it to a diagram, right? And the diagram has intuitive meaning. It really describes a process, as I said, of exchanging a gauge particle, and if you want now to do perturbation theory with this, you can think of just giving you a head like an advertisement why it might be useful to use a graphic language, because then you have to combine a diagram that has many such VQs, right? And then what you get, you can guess it just from what kind of graphs you can plot, okay? And already see the answer. So it's giving a shortcut, a conceptual shortcut, just because we can use a graphic language. Okay? This, by the way, is called the Feynman diagram. So Feynman invented this idea. All right. So, good. So this is for this is the form of the operator that we would like to work with in order to describe, for example, electrons in a metal. In a metal, K is more or less a good quantum number, 3 electrons, and there is a Coulomb interaction, but you don't know how to solve it exactly. You don't know how to diagonalize the Hamiltonian that has both H naught and V, because the interaction has a sum over many indices, and you can see that it's not easy to see a state that is an eigenstate, okay, of both H naught and of interaction. And then you want to try and do perturbation theory, and that's the simplest thing you can do, and this will be the first thing that we'll do. But I'm already telling you, naively, it's not justified, just because if you look at the numbers for the energy scales, the Coulomb interaction is not small, okay? But there is a more sophisticated reason why in the end it is for metals, it is a good approximation to do perturbation theory. For more complex materials, for oxides, for 2D materials, for twisted bilayer graphene, all sorts of more exotic materials, it's definitely not allowed, okay? And really the more interesting materials around us are not metals. They have other states, you know, Mott insulators, the superconductors, charge density wave, and have also magnetic materials, right? So all these come from interactions. Okay, so but we are going to start with the perturbative approach, and for that, let me just give you an idea how we would like to proceed, because there is still some complication. And as I said, let me rewrite again the H naught, the non-interacting Hamiltonian, and I actually I want to once again assume put in a sigma if you like. I want to write a general lambda, a lambda. Actually, let me even be more general. Just have lambda, okay? So, and lambda, if you like, for metals, it's going to be K and sigma, or actually, for any clean crystal, lambda is K and sigma, but this is what it is. Now, and the epsilon lambdas give you some spectrum. So let me plot it again. It may not be equal spaced, it may be complicated, but there is some spectrum of energy levels. Okay, so this is epsilon of lambda. And we already discussed what is the ground state. to get the ground state, you have to give me either the number of electrons or the Fermi energy, the chemical potential. In both cases, both are related, right? So, and let us just assume that there's some Fermi energy that is given by chemical potential if temperature is 0, and these are all occupied, each by 1 electron. Okay, maybe they are the general C's, but here I'm plotting all the numbers. Okay, so the ground state is a product of lambda. Let me write it like this, where the meaning of this is that it obeys that energy is smaller than E Fermi. Okay, so lambda belongs to the Fermi C, or to the Fock state. They all have the same initial F, and of A dagger lambda acting on the vacuum. Okay, this is the ground state, and in principle. And now let's assume that we want to do perturbation theory on VEE. How do you do perturbation theory? The first order in perturbation theory, I want to assume in perturbation theory, let's assume that the ground state, this is the ground state of H naught. So the first order correction to the energy is just expectation value of VEE inside this ground state, right? So this is what we want to calculate. Let me call it 1. Okay, this is the first order correction.
Right, here it's by definition non-degenerate because it's fermion.
What? Sorry?
Here it's by definition non-degenerate because it's fermion.
No. I mean, when I plotted the very arbitrary level spacing. So some of them may coincide because if lambda includes the spin and the energy doesn't depend on the spin because there's no magnetic field, then you'll have 2 states for each k. But still, there's different sigmas or different quantum numbers. Okay, so the quantum number has 2 indices. So when I denote by lambda the quantum number. Now, for this purpose, I also don't care if they are degenerate or not, okay? Because all I care is that, if this energy is obeyed, it's included in one operator, and each lambda is at least either sigma or k or both are different, okay?
Yeah, but then if you want to correct the wave function.
Let's not worry about the wave function, but yeah, you write it, okay, the wave function will have, but the corrections to the wave function will also want to write in terms of Fock states, but all the states, I mean, if I just split it more explicitly in terms of k and sigma, you'll find here a product of all k's and all sigma of ak dagger k of up and ak down, and do it for each k. Okay, right? I mean, if lambda is indeed this, if you want to be more specific, then this is the product over all k with epsilon k smaller than Fermi, and for each k, I have actually 2 states with the same energy, but both of them exist in my ground state. Both are occupied if the energy is smaller than before. Okay? Okay, so that's just splitting of the lambdas to k's and sigmas, but But I want to, for simplicity, let me just leave it as one index that has encoding everything, and I really don't care about how the spectrum looks like, whether some states are degenerate. I don't care, because it doesn't play a role. Again, I only demand that they're all occupied. Okay? You're right that some perturbations can split the degeneracy, but in our case, it will happen only if you're close to the Fermi energy. So that's where I'm heading, okay? So actually, now let me, so in principle, just straight, quote, straightforwardly, I should take this operator, and it's a relatively simple two-body operator. It only changes the state of two, each term here changes the state of only 2 electrons, okay? And then I take it and I apply it on this, this ground state. And then I want to calculate expectation value, so I first need to see what this operator does when it acts on my ground state. But at first sight, it looks like a complicated calculation, because what you have to do, why is it? It looks complicated, although it's actually not so much. Because in this product, I have a macroscopic number of particles. Okay, this is what we are living in the thermodynamic limit, right? Macroscopic number of particles. So, in principle, to do calculations, what I need to do, use the commutators, shuffle the annihilation operators to the right, and I mean, you'll do such exercises for small number of particles in your home. But here I have 10 to the 23 particles, and each time I have a different momentum. So I have also an infinitely many terms in my sum here. So it looks a bit complicated to work in a representation where I keep track of all the particles, most of which don't do anything because they are buried deep in the Fermi sea, right? So in fact, if you think of it, if this is really a perturbation, what it does is it only it can only make small changes that change the state of the particle. Now, I cannot make a small energy excitation here, right? Right. So if you apply the momentum. If you apply the density operator rho q, which, as I said, it's a scattering, right? So it changes the momentum and it creates an excitation. It changes the energy of the electron. But I cannot, if I want to increase the energy by a little bit, I cannot do it because all the states here are occupied. Where do I have a chance of getting something? Only if and again, I'm talking about small energy, it's a small momentum transfer, only processes that are very close to the edge of the Fermi sea has an effect. Because then you can take an occupied state and take it out of the Fermi sea. Okay? So you have to account for very few or very narrow shell close to the Fermi level that does something. And therefore it's not useful to compare everything to the real vacuum, like the real empty vacuum. Instead, it will be more economic to think of the field Fermi sea, this ground state, as the new vacuum. Okay? And this is what we're going to do probably next time. So I'll just give you a head up of the idea. What is the idea? You want to define the Fermi surface will be your vacuum. But if this is the vacuum, you have to define new annihilation operators that are, and of course creation, that are annihilating this vacuum. And they are not necessarily going to be A's, A lambda, okay? In fact, we're going to see that they're going to be some combination of A lambda and A lambda dagger. But the idea is to switch to a new vacuum, and a new vacuum comes as a package deal with new definition of your annihilation operators, and therefore with your creation operators, okay? And with respect to this new vacuum, the calculation will become a bit simpler because you only have to account for the small processes in fact, you're going to work in a language where the number of operators that you have to sandwich is small, is at most 4 and not 10 to the 23, okay? Okay, so that's the idea, and how to do it in practice. We'll see actually 2 weeks from now, because I don't know if you all saw my announcement, but next week I'm not here, so Sarah will give 2 tutorials in a row, and then we're going to get a lecture 2 weeks from now with me. Okay, so see you in, have a good weekend, and see you in 2 weeks then.
Yeah.